Hello, everyone, and welcome back to the Cisco Optics Podcast, where we talk about pluggable optics for networks. Multi-modeFiber has been the workhorse for fiber optic communication within a data center for years, as well as a choice for Ethernet backbones in office buildings. It has a rich history that goes all the way back to the first optical fiber standards when 100 megabits per second was a huge data rate. Anybody remember those days? This is episode 56, and we continue our conversation with Hao Dong, Market Technology Development Manager for Corning's optical communications business. We get into the various multimode fiber standards, transceiver wavelengths, and future transceivers for multimode fiber. Hao Dong is a Market Technology Development Manager for Corning's optical communications business. Within this role, he focuses on technology and market trends to identify, evaluate, and develop leading optical network solutions that form the backbone of today's connected world. Hao has over 18 years of industry experience and has held various positions in engineering, development, and marketing within the fields of optical components, fiber lasers, and optical communications. Hao holds a Bachelor of Science in Physics from Wuhan University and a PhD in Physics from the University of Connecticut. One quick note before we start, you'll hear Hao mention the need for a 100-meter reach fiber. Since we recorded this, Corning has actually released such a fiber. It's their ClearCurve OM4 XT multimode fiber. And now join me as I talk with Hao Dong.
OM3 and OM4 as a laser optimized multimode fiber. That was considered as a workhorse for the new installation nowadays.
So what did they optimize? So OM2 was for LEDs. OM3, what was the optimization? Like what's different about it that makes it optimized for lasers?
As I mentioned, nowadays for 50 micron multimode fiber, they are grid index fiber, right? So the reason behind that is with the grid index fiber, it will trying to mitigate the model dispersion, right? So higher order mode at the edge, seeing less refractive index, and fundamental mode or lower order mode in the center. They follow a shorter path, but they see a higher refractive index so that the speed is slower.
Oh, okay.
So with this arrangement, eventually it kind of like a balance the time difference, right? So that's what's going to happen in the ideal world, in the perfect world. However, in practice, it's very difficult to control the profile, precisely to match your need, right? So that's in terms of the control, there is a control of the profile. There is a difference between OM2, OM3, and OM4, and eventually, it gave you a different information carrying capability or the capability to address those model dispersion issues.
So when you say the control, are you talking about even on paper, it's difficult to come up with a graded index design that perfectly compensates the longer path or the shorter path but a higher index versus the higher index but the longer path?
Yes, on paper, the standard defined the different values. For example, for you must have heard of OM3, the EMB values at OM3, that's 2,000 megahertz kilometer. For OM4, that's 4,700 megahertz kilometer. So these are the values for the EMB or the so-called information carrying capability, right? So, when you think about how to link those values with the profile, so it's very difficult to quantify the profile details. But that's give you an idea how the information carrying capability and eventually with the different fiber, how it will impact the optical transmission performance.
So what about OM5? Is there anything you want to say about OM5?
Yeah, sure. So OM5 is it's a relatively new type of multimode fiber, right? That was basically the OM5 was introduced to support short wavelength division multiplexing, right, or SWDM. I think it was introduced by TIA standards in 2017. But essentially, OM5 could be considered as a subcategory of OM4 fiber, right? Because if you look at the EMB values for both OM4 and OM5, they share the same effective model bandwidth or EMB values at 850, which is 4,700 megahertz kilometer. The only difference between OM4 and OM5 is that for OM5, they also specify the EMB values at the 953 nanometer because, like I said, the OM5 was introduced for SWDM, right? So for SWDM, you will need the wavelengths ranging from 850 all the way to 940, and that's why you need to define. You need to specify EMB values at higher wavelengths edge.
And for people who aren't familiar, SWDM is the a transceiver type where 4 different wavelengths are multiplexed onto a single multimode fiber, right?
Exactly. Yeah. Typically, I think people would consider the industry consider 850, 880 nanometer, 910 nanometer, and 940 nanometer. So all of the 4 wavelengths will be, through WDM. You combine them together and sending the signal through the one single fiber strand. The benefit, of course, is very obvious, right? You could save the use of fiber, but the problem is that I think there are 2 problems. One is that the cost is much higher, right, comparing with a parallel or even BiDi. And the second thing is it doesn't support a breakout. So,
so sorry, just to recap. So, it sounds like OM4 was spec'd only at 850, you said, nanometers?
Yes, OM4 is only specified at 850 nanometer.
Okay.
Yeah.
And so that predated SWDM4, I'm guessing, because at the time of OM4, there was no need to specify at any other wavelength. Right.
That's right. Yeah, because most of the multimode before SWDM, most of the multimode, will be based on 850 only operation. Right? So, even though besides 850 only and SWDM, there is another multimode application which is called a BiDi. But the BiDi typically is based on 850 nanometer and a 915 nanometer.
915, not 950.
915, yes. 850 and 915. From that standpoint, you also you don't really technically you don't need the OM5, right? OM5 sounds like overkill for BiDi.
Because OM5 goes all the way out to 950, whereas BiDi only goes out to 915.
That's right.
Okay.
Yep.
What are your thoughts on future-proofing when it comes to multi-mode fiber? Because we haven't really talked about the future that much. We've talked about history quite a bit. But what do you see in the future, and what thoughts come up when you hear future-proofing?
Well, I think to answer the question, we probably could look at the trends, right? What is driving the trends in data center? Obviously there is a bigger driver for higher speed. Right?
Sure.
Today, if you look at the switch, right, 25.T switch, and even a 51 terabit per second switch capacity is, being deployed. So for higher switch, obviously it will be driving the higher speed of transceiver eventually. So for single mode side, 100G per LAN based client transceiver, I think that's a new norm, right? If you think about the 400G transceiver, there is a 400G DR4, FR4, LR4, those transceivers are based on 100G per lane single mode already, right?
Mm-hmm.
So obviously, for short reach application, for multimode, we need something to be compatible with that. So in our opinion, I think it's critical to sort of to have a 100G per lane based on multimode available, and the distance wise, it should be able to cover the distance up to 100 meter.
Because that's what people
so
people are accustomed to deploying at the lower speeds, up to 100 meters in their data centers using multimode fiber, right?
Exactly. So that means two specific points. One is that from the optical standpoint, it need to be 100G per lane based, and from the reach standpoint, it need to cover 100 meter, especially for OM4, right? So speaking of the future proofing, I think that's what the future should look like for multimode. Again, 100G per lane based with the distance up to 100 meter. If you look at what the standards or MSA doing, basically they are following this path, right? For example, IEEE defines 850 nanometer based application for 100G per lane, right? IEEE AO2.3 dB. I think this standards start about 2 years ago, and by September 2022, the Standard Association is already approved that.
Did you
now
say
100G per lane?
Did you say 100G or 400G per lane?
Well, it's 100G per lane based,
Okay.
But the data rate for the transceiver will be, I think, all the way up to 400G.
So 4 by
400G
100G. Basically an SR4.
That's right. That's right. Yeah.
SR4 meaning like there's 4 fiber pairs. So each fiber pair is a duplex, 100G.
Yes. So in total, you will need 8 fibers for the
Right.
module. So that'll be 8 fiber based solution for 400G data rate.
And this is something that OM4 can support?
Well, so that's a good question. So IEEE defined OM3 for 60 meter, and OM3 for 60 meter, OM4 for 100 meter.
Mm-hmm.
So like I said, for future proofing solution, it need to be supporting the distance up to 100 meter, right?
Yeah.
But if you look at the history, the industry basically follow kind of like a golden rule: 70 meter OM3 and 100 meter OM4, right? For example, at a 400G, that's a case for 100G SR4. It follows 70 meter OM3, 100 meter OM4, and a 400G, even 400 BiDi follow the same arrangement. But the problem is that for this newly defined IEEE standards, the OM3.
That was the 5th part of my conversation with Hao Dong. Next time, we'll get into future high-speed standards. We have a new website. It's optics.podcastpage.io. You can either listen there or use the same podcast platform you've been using all along. Please subscribe. Better yet, leave a review, especially if you've been using Apple Podcast. Remember, we're part of the Cisco Podcast Network, where you can find other great Cisco podcasts too. We also have educational videos on YouTube. Just go to youtube.com and search on Cisco Optics. Thank you for listening. This is Pat Chow, Product Manager at Cisco Optics. The next episode is part 5 of my conversation with Hao Dong. Until next time.